Hello, it's Keith here, and this is lesson 1 of the multi-platform series of my 6502 assembly programming tutorials. The multi-platform series is where we're looking at pieces of code which will basically work on any 6502 system. Now, today we're going to be looking at a speech synthesizer that I've ported from the Z80. I've got it working on a few of the 6502 systems, but really it's fairly trivial to port it to another 6502 system if you know how to output digitized samples. All you need to do on most systems is just set the volume according to a 4-bit sound sample. Now, this was actually ported from the Z80, and usually I write my own code, but I don't know enough about speech synthesis. So in this case, I've actually disassembled another program. Basically, while you're welcome to download the source code and use it from my point of view in any way you want, this was originally distributed as a program called Speech on an Amstrad Action cover tape, and it was copyright 1986 Superior Software. The exact same program, strangely, was also released as the speaker by Xavier in a magazine called Grosset, I believe a French magazine, in 1991. Now, if you are concerned about either of those people coming back and sort of suing you for copyright, then you shouldn't use today's source code. I'm providing it for educational purposes. You can use my code for whatever you want, but I didn't write today's, unlike the rest of the stuff in my tutorials. So that disclaimer out the way, we're going to look at this now. So today we're going to be looking at it on the PC Engine. It does work on a variety of other systems, including the C64 and the NES and things. But okay, let's hear it. So in case you didn't understand what that said, it said, "I am a PC Engine, you are a worm, you will bow to my 6502 superiority." So it changes the platform and the processor depending on the version. Today 6502, and we've compiled for the PC Engine. Now, if you look at the screen here, I've just paused it for a second, you can see that we've got this weird phonetic version, IY4, AEM, AE, PEE4 and so on. Now, this is the converted version of the text that the software is going to say, and it's just corrupting the screen now. That is that we're going to see the code that actually prepares the string for speech and converts it today into phonetics. Next time we'll look at the actual speech synthesis, the wave sample selection routine. Today we're looking at the conversion routine. Now, just as a sort of disclaimer, you saw some corruption on the screen there. I did a very crude job of the memdump routine just to show the actual code there. To use this software, you would typically disable that. So I'm just going to run those lines out, and if we just run it again, you now won't see anything on the screen. So that corruption and things wasn't anything to do with the speech synthesizer. That was just my testing routine, so you could see the converted phonetics. Okay, well, let's go over to the source code and let's take a look. Okay, so the file we're looking at today is speech.asm, and this is the finished 6502 version of the code. Now, at the start of our code, we're defining some variables memory here. The code itself uses some variables along the way for the calculations, and it also stores 2 versions of the string. Now, the first one has simply been basically converted to uppercase, not much more than that, and then the second one is converted into sort of the phonetic equivalent for the sample selection routine to pick the appropriate speech parts to actually say it. Now, those are stored at txt raw string, and the amount of memory you'll need there simply depends on the length of your string. Now, here is the string that we are speaking today. So you can see it's different in all cases, and in some cases I've had to make some tweaks to make the speech come out appropriately, because this speech synthesizer hasn't been coded with every possible phonetic conversion. Now, at the end of the code here, if I find it, here we go. So this is the phonetic conversion table that it uses. So basically these are pairs of 0-byte separated strings. The first one is the sort of raw string, so David there in normal English there, and then the converted version DAYV IDH there, or HD there. So as I say, they're pairs, unconverted and converted, and we've got a lookup table here to find the various letters that those strings start with, and we'll see that in our code today. So that's how we're doing the conversion. Beyond that, you've got some stuff related to the wave samples that we're going to see in next time's lesson. So we're using the routine say string from HO to do the conversion. Our initial string is in normal text and it is 0 terminated. So let us take a look at this routine. The other thing we're passing is we're passing a number here. This is actually the speech speed. If I change this to 15 and I run this again, And you can hear the pitch is much higher there, and it also plays faster. So that is what happens if we play with that. 15's a bit high. That's basically the highest it will go. Okay, so let's see what, say, string from HL is doing to prepare the string for speech. So the first thing we're doing here is we're taking the value in the accumulator, the speed, and we're converting this into a value that the routine can use. It's basically used as a sort of loop during the speech synthesis part, the speech playback part. So that's what's going on there. Now, the text raw string is the string that has been converted. So our source string is in the 0 page entries H and L. That's a pair in the 0 page I use to mimic the Z80 registers. As I say, this is ported from the Z80. And so what we're doing here is we're first storing a space at the start of the string. It uses spaces to separate the words there. Okay, and then what we're going to do is we are going to basically copy all of the characters from our source string into our destination here. And we're also going to remember the last character we saw. Now, part of the code, it checks the last character and it changes the pitch for questions and full stop sentences. If the sentence ends with a question mark, the pitch changes up on the last two vowels. If it's a full stop, it changes down. And so that's what this is doing here. And we're getting B is going to be the last character, and we store that for later on in our speech playback routines to decide. We're also making sure the sequence ends with a space followed by a character 13. The initial string was terminated by 0, but the rest of the code is terminated by a character 13. Why? I don't really know. As I say, I actually disassembled this. I reverse engineered it from a compiled binary. The choices I've left the same unless I felt that optimizing it in a different way was more effective. So in a lot of cases, it simply works the way it used to work. Now, one thing I should point out with regards to optimization is I'm not the best 6502 programmer, but in this case, more than most, I've actually tried to make some optimizations to the code simply because of the limitations of the size. Originally, the PC Engine version was so big it wouldn't fit in a single 16K block. I've actually reworked the code so that doesn't matter, but for some of the systems have very limited memory available, and so I was trying to make more effort than I usually do to optimize it. Now, I've tried to use the X and Y registers where appropriate, and I've done some other things like create subroutines to do common little tasks. But one thing I've done this time that I don't usually do is using relative branches for when I actually wanted a jump. So the classic 6502 doesn't have the BRA command, the branch always command, the 1 byte plus 1 offset byte, so 2 bytes in total, a command that always branches. We have the jump command, but that takes 3 bytes. Now, in a lot of cases, we will know what the actual flags contain. For example, if we've branched, if the 0 flag is set, then we know the 0 flag is clear if we are still running the code. If we've loaded in a value that we know will never be 0, then we can use a branch if not equals, and that will always branch. And so I've been doing quite a bit of that kind of thing, using conditional branches in cases that I know they will always branch, and that's simply to save that 1 byte over the jump command. I don't usually do it because it makes the code confusing, but in this case space was becoming a problem, and so I have tried to optimize a little bit more than I usually would. Okay, so what we're doing here is we've basically transferred all of the bytes from the source to the destination, and then we've remembered the last character in the process, and we've made sure that the string ends with and starts with a space and a character 13. We're then going to run this charfix routine. So let's take a look at the charfix routine and see what that does. Okay, so basically what this does is it converts lowercase to uppercase, and it's also removing the slash symbol, which has a special symbol within this routine. The slash symbol is a sort of, I don't know quite how to describe it. It's a sort of rather odd sort of distorted phonetic that it puts in. So that has a special purpose, and so it's being removed in this case. Now what we're doing here is we're checking if the string is in uppercase. If it is, then we're carrying on. Otherwise, we're converting to uppercase with this calculation here. Now this is one of these cases here. Now usually I would set the carry here and then subtract 20 in hexadecimal. In this case though, we know that the carry is clear, and so that means that we are effectively going to subtract 1 extra than we would usually want to. However, because I know that, I'm actually reducing the amount that we're subtracting, so we're effectively subtracting 1F here because I know that carry is actually clear here. So that is saving me that byte by that sec command, but it makes the code a little bit more confusing. So that's what I've done there. That is effectively converting us to uppercase. So here we are writing entirely uppercase characters here. This is for when we have the case of the slash, we're just converting that to a space there. So that is fixing the string and converting it into uppercase. So that's what's going on there. Okay, so that's that routine there. That's just converting us to uppercase. Now, once we get to this point here, basically what we've done now is we've got the string in uppercase, and we're then going to convert that into phonetics. And so we're going to store the phonetically converted string immediately after that first string. The original code stored it in a totally different memory location, wasting a lot of memory, storing these various values all over the place. So I've combined them into right next to each other. So what we're doing here is we're basically adding the offset in the Y register to the DE pair, and then storing that in H and L here. So HL in the 0 page are used for the next part, which is the conversion to phonetics. Now, once we do that conversion to the phonetics, we drop into the speech routine here, which we're really going to focus on next time, but I'll just quickly discuss this part here. So we're initializing these variables here, which are used for distorted sounds. There's a distorted routine for SS kind of sounds, so that's used, and those variables are used by that. And then this routine here is just storing the current position of the string for the next speech sequence, checking for the end of the speech sequence, and then running this routine here, which is the one that selects the samples to make up the various phonetic parts of the speech. But it's those phonetic parts that we're going to find today with this convert to phonetics routine. So let's take a peek at that. Okay. So what we're doing first is we're storing in raw string pods the position of the string that we're next trying to convert. Okay, so what we're going to do is we're basically going to first reset the 4 bytes of these switch addresses. Now, there's 2 of these switch addresses, each is 16 bits, 4 bytes in total, and I've put them neighboring to each other in memory, and so I've cleared them with this little loop here. Now, these switch addresses are used to remember the last 2 positions of the vowels in the speech for when we do that pitch up or down shift for questions or full stops. So these are going to be used during the rest of their code, but they're being initialized to 0, I guess, just in case there's no vowels in our speech. Pretty unlikely, but again, this was something that the original code had. I've not taken anything out except for where it doesn't reduce the functionality of the result, so this has been left in. Okay, so that's clearing our data here. That's storing the address of the translated string again, and then this translate to phonetics will do the conversion, and then we are finishing the translated string with a character 13 once again. So let's see this translate phonetics routine. Here it is. So what does this do? Well, what it's going to do is basically read in the current position of the string that we're converting here, and it's going to check if the next character is a character 13, the end of the string, and if it is, we're going to return. We're just jumping to a return command up here. Otherwise, we're going to find a matching entry, and we're then going to transfer that entry to the converted string, and we're going to keep doing that until we are finished. Now, how do we look up an entry? Well, basically, what we're going to do is we're going to use the lookup table of the conversions, and we're going to pick the most appropriate conversion. So what we're doing here is we're seeing if we are looking up a letter or a non-letter. Now, if we're looking up a non-letter, something below A or Z or after Z, that square bracket is just after Z, then we are going to jump to this lookup non-letter, which will select either the space lookup table or the numbers lookup table, so for whole words and numbers and things like that. Otherwise, we're looking at something with a letter. Now, what we're going to do is we're going to look up the memory address within our lookup table. So where is it? Here is our lookup table. So we've got one entry for A to Z here, our letters, and these point to the various sections within this for the section starting letters. And you can see also we've got the one starting numbers here. And we should probably have programmed in 6502 there, but I haven't done so, so maybe you want to do that, do a better job than me. And we've got the one for starts of words and whole words here with spaces. But generally, this A to Z entry table is what we're going to be using. Now, what we need to do, of course, is we need to select an entry within this table for our letters. Now, each entry is 16 bits, so that's 2 bytes. So we are taking our letter that we want to find, subtracting the letter A, again -1 because of we know the state of the carry there, and so we're effectively converting A to 0, then we're multiplying by 2, so B would become 2, and that is now an offset within that 16-bit address table. So we're then adding the lookup here, and setting conversion address to the address within that table of the conversions we're going to do. Now at this point what we want to do is we want to find the most appropriate match within that table for the string we are currently trying to find. Now basically this table it continues with all of these possible options, but the final option here is double question mark. Now question mark will actually match anything, and a question mark in the match will return the character that was passed. So this is basically a catch-all if nothing else has matched. So we know that we will find a result even if the result is simply whatever we were initially passed. So here we're loading the string position that we are looking to convert. Here we're loading our converter. And what we're basically going to do here is we're going to compare each entry in our conversion table with the entry in the string we're trying to convert. And if it matches, then basically we're going to do the conversion. If it doesn't match, then we're not. So we are loading in our source. We've got a test for if we found a space in our source. We've got the catch-all question mark here. Now the question mark is a bit tricky, where if I can find out where that goes to. The code's a little bit confused because I've had to sort of make some of the code a bit jumbled up so that the relative branches can work as well as work effectively. If I put everything after the branch, then soon I'd go over the 128 limit. So here's the question mark code here, and what we're basically doing here is we are checking if the source was the end of the string, and if it's not, we're then storing that source in char from string, because as I say, this is a wildcard and it will support anything. Now there can only be one question mark in a string. You can't have two neighboring question marks in a string because we're only storing a single character there. So what we're doing here is we're seeing if it matches. If it does match, we're continuing on to the next entry, basically repeating until we've found a 0. Now if we find the end of the string, end of the comparison string, and we've not found a failure, something that doesn't match, then we've found a valid conversion. Otherwise we keep going until we find something that doesn't match, and basically if we find something that doesn't match, we go here, we store the position that we ended up at, we clear the carry to tell the calling routine that we didn't match, and we return. If we do find a match, then we set the carry to tell the calling routine that we've found a match. Now once we find a match, we need to move back to the start of this match. So that's what's happening here. We are basically updating our registers here, moving back to the start of the string here. Now when we found our match, we are checking with this valid phonetic test here to make sure if the character that we are currently looking at is something that we can indeed convert here. So that's what's going on here. We've got our range here. Now there's a little bit of code here that I have to admit I'm a little bit confused by. As I say, I didn't write this, I just converted it. And so basically what it's doing is it's moving back 3 characters, and it's updating the HL source in the source string, depending on if 3 characters back is the 0 in the destination. So I guess this is just because some of the strings are different lengths. This seems a little bit odd to me, but again, I didn't try and change the original code beyond what I could see to clearly to optimize. So this has just been left as is, and as I say, it does seem a little bit odd to me. Now, if we found a match, we're going to just return. If we've not found a match, we need to do this again. So what we need to do is we need to skip over the current comparison that we were trying to use because it didn't work, and we need to try the next one, because remember, the final one will always succeed. It's a catch-all, so it will definitely succeed. Now, how do we skip a failed match? Well, each entry within the table is 2 pairs of 0 terminated entries. So to skip over an entry, we need to find 2 consecutive 0 bytes. So what I'm doing here is we are using HL as our source comparison, and we're going to find 2 zeros, and I'm using the X register to count those zeros that we found. So what we're doing here is we are going to scan until we find the first 0. That's what this loop here is doing. And then once we find a 0, we are decrementing the X register, and when that reaches 0, we've found both of our 2 zeros, and so then we're ready to start scanning again. So that's what we're doing here. We're storing our updated conversion position. We've moved along to the next entry, and we repeat. And as I've said before, something will match, because that last entry of a single question mark character will match literally anything. Now, once we've found our entry with phonetic lookup entry, we're using the transfer entry routine. So basically, it's pretty straightforward. All we are doing is we are loading in the conversion from our found match. And then what we're going to basically do, well, once we get to a 0, we've finished the string. If we find a question mark, then what we're doing is we are loading in the character that we remembered earlier when we found the question mark in the source comparison, because remember we set that character char from string to the equivalent position in the. So this is basically going to copy a character of any kind from the source string into the phonetic conversion here. We're then storing that phonetic conversion, and we are repeating here until we are done. Now, one final thing we are doing during this is we are checking before we store the value with the vowel switcher. Now, what the vowel switcher does is it's trying to find the last 2 vowels within the string. Remember I said it changes the pitch up or down for the last characters if there's a question mark or full stop at the end, and that's what this is doing here. So we're seeing if we found a vowel here. If we have, we jump down to this HL switcher. Now this uses a toggle, so this is either a 1 or a 0, and this is basically either storing the current value in entry 2 or entry 1, and it swaps them over basically whenever it finds another vowel. So that's what's happening here, and these are used later on in the speech playback code to find the to find the position of the sample that is the last 2 vowels, and it changes the speed accordingly depending on, as I say, whether that last character is a question mark or a full stop. So what you saw today is the code that converts the text in human form, you can see there, into the phonetics that you can see on the screen here. Now next time we're going to look at the speech synthesis routine that plays these kind of sound samples. So there we go. So if you like what you've seen, please like and subscribe, because we're going to come back and see the speech synthesis next time. And as I say, you're welcome to go to my website and download today's ASM file and do, as far as I'm concerned, anything with it that you want. Just bear in mind, as I say, this is a disassembled piece of code. It's not something I've written, so you have to use it at your own risk from that point of view. I highly doubt that the company that wrote this in the 80s and 90s really care about it anymore, but I can't give you assurances that aren't mine to give. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.